Iron cycling and its effect on permafrost greenhouse gas emissions. This is straight from the Ornell website. The direct link to the page is in the description below. The interaction of elemental iron with the vast stores of carbon locked away in Arctic soils is key to how greenhouse gases are emitted during thawing and should be included in models used to predict Earth's climate, Oak Ridge National Laboratory scientists found. Researchers set out to explore and model the chemistry going on as the Arctic permafrost thaws in response to global warming. Northern permafrost soils contain an estimated 1,460 billion to 1,600 billion metric tons of organic carbon, about twice as much as in the atmosphere, according to the National Oceanic and Atmospheric Administration. Chemical processes in the soil control how organic matter decomposes and is stored in soils and whether it converts to carbon dioxide or the more powerful greenhouse gas methane when released into the atmosphere. Arctic soils are typically organic rich and often have a high iron content, frequently visible as rusty deposits in flooded soils in the region, says Ornell modeler and principal investigator Benjamin Solman. But current Earth system models do not take iron cycling into account when predicting the climate warming potential of thawing permafrost. A new chemical reaction model created by Ornell incorporating iron, carbon, and oxygen concentrations and soil acidity suggests that iron cycling can have a profound effect on whether carbon dioxide or methane is produced in repeatedly flooded Arctic soils, as described in the Journal of Geophysical Research, Biogeosciences. Thawing permafrost can be subject to dynamic hydrology, making redox processes an important factor controlling soil organic matter decomposition rates and greenhouse gas production. In iron-rich permafrost soils, ferric iron can serve as a terminal electron acceptor, promoting anaerobic respiration of soil organic matter and increasing pH. Current large-scale models of Arctic carbon cycling do not include iron cycling or pH interactions. Iron can be used by soil microorganisms as a substitute for oxygen under waterlogged conditions, which produces carbon dioxide using a strategy that is typically thought to compete with methane production. Conventional wisdom says that if there's more iron in the soil, it should reduce the amount of methane that's produced, Solman says. But we found that's not necessarily true. Under the right conditions, we see a synergistic interaction where iron cycling changed the acidity of the soil in a way that also made it more advantageous for methane production. The effect of iron cycling on methane production depended on the availability of easily decomposable carbon. When iron reducers competed with methane producers for a small amount of available carbon, methane production declined. When easily decomposed carbon was abundant, iron reduction enhanced methane production by decreasing soil acidity. The scientists found that repeated flooding and drying of soils can be a key driver in permafrost greenhouse gas emissions by replenishing forms of iron that are gradually depleted by flooding. The models are based on data gleaned from incubation experiments with soils collected in Alaska's permafrost as part of the Next Generation Ecosystem Experiments Arctic, or NGEE Arctic. Results from those experiments highlighted the importance of iron cycling and led to the modeling work in what is known as MODEX paradigm, Solman says. MODEX, or the Model Experiment Approach, integrates observations and measurements from experiments with computer models of the same processes in an ongoing conversation that informs both the improvement of models and the design and interpretation of experiments. This loop ensures that models reflect the latest findings on critical systems, and the simulation in turn identify knowledge gaps and guide future experiments. Typically, soil research has focused on either dry or wet conditions, but not both, said Ornell's Elizabeth Herndon, whose soil and water sampling work in the Arctic provided data for the project. The reality is that soil saturation can fluctuate a lot. You'll have a rain event, and that results in oxygen-depleted conditions where microorganisms are essentially breathing iron to drive their metabolism. But when the soil dries, oxygen is reintroduced. In this paper, we want to explore what happens when you have these widely varying conditions. The challenge with the project was moving to a model based on more than just the carbon cycle. You essentially raise the bar of how much data you need to make sure that the model is giving you useful predictions, Solomon said. That's where having these rich measurements from laboratory incubations of Arctic soils was very important for producing data about how the iron cycle and soil acidity were changing over time. From an experimentalist point of view, having discussions with modelers and deciding how to quantify certain processes helps me to think about how we can structure our experiments to get the information we need, Herndon said. She stressed to modelers the importance of representing specific processes in the simulation, including the presence of iron oxide minerals and the environmental fluctuations that can trigger chemical changes in the ecosystem and alter carbon emissions. Next steps for the research include incorporating the chemical reaction model into the land segment of the U.S. Department of Energy's Energy Exascale Earth System model. Solomon said he also wants to test some of the new model soil chemistry hypotheses at NGEE Arctic field sites and then integrate resulting new data into the model, continuing the MODEX cycle. These two halves of the MODEX loop really help fill in some of the missing pieces that can come out of either modeling or experimentation, said Solomon. If you're doing modeling that's not well connected with measurements, it's easy to diverge a bit from reality and end up working on questions that are not important on the field scale. Or you end up with a model that is not well grounded enough to behave like a real system. In terms of planning experiments, modeling is useful for generating hypotheses and narrowing down some of the specific processes that seem to have the biggest impact on scientists' ability to answer questions that matter, Solomon said. In this instance, what we've found so far can help us predict how these carbon dioxide and methane fluctuations will change over time, especially given hydrological patterns. This detailed knowledge of the permafrost soil chemistry improves our ability to predict the impact of the warming temperatures. Solomon expects to employ a similar approach to other hydrologically dynamic ecosystems Ornell is studying, such as coastal wetlands, to better understand the carbon cycle. UT Batil manages Ornell for the Department of Energy's Office of Science, the single largest supporters of basic research in the physical sciences in the United States. The Office of Science is working to address some of the most pressing challenges of our time. For more information, please visit energy.gov/science. Stephanie Sia.